Welcome, everybody. Thanks for attending today. My name is Jennifer Griffith, and I work at NEMOA, which I hope, Anthony, do you see the NEMOA website on the screen?
I do.
Good. Okay, so everybody should see that. I work at the Northeast Waste Management Officials Association. We are an association of the 6 New England states, New York and New Jersey. We were formed by the governors back in 1986. And, well, actually before that, and we were formally recognized by EPA as an interstate association in 1986. So the waste programs as well as the cleanup programs work together through NEMOA. And one of the main priorities for the waste site cleanup programs is training and information sharing, and PFAS has been a priority topic for them since 2016 as a region. So this webinar today is just furthering the information and training on PFAS. So welcome. I am showing the website as well so you can understand what NEMOA is, but also to show you where the presentations from today will be posted and where you can find a wealth of other information. So the main NEMOA website is nemoa.org. Then you go to waste, click over here. Our website also is very ancient. We haven't been able to update it, but hopefully we will at some point. You click on waste site cleanup, you go to events, and then we've got some upcoming events. Here's the webinar from today, and then also past events. So we've done a lot of other PFAS. We've done 3, this is the 4th PFAS webinar in this series so far. We also have done some record compliance. We've got a lot of other, for people that work in waste site cleanup, a lot of other, we've done workshops, lots of different other, here's PFAS webinars that we did last year. So a lot of different information for folks if you're interested. And like I said, these presentations from today will be posted probably either later today or tomorrow. So we're going to do a format where we're going to have the first presentation, then we will do questions about that presentation, then we'll do the second presentation and questions. But you can type in questions at any point. You're going to have to type them in. We've got a lot of people attending today, so we can't have people ask them verbally. So in your control panel for GoToWebinar, that you have, there is a question topic, and you just click on that and then type your question in, and that will record your question. You can do that at any point. You don't have to wait until the presentation's over, and then I will be keeping track of those, looking through them, and then I will ask the questions of the presenter. So I think that's it for the logistics on the webinar today. So we'll get going. I'm going to introduce Anthony and make him the presenter. So Anthony Drurin is the administrator of the Residuals Management Section for the Wastewater Engineering Bureau at the New Hampshire Department of Environmental Services. Before working at New Hampshire Department of Environmental Services, or DES, Anthony was a senior project manager in the residuals management industry, managing Class B and Class A biosolids land application and the bulk landscape supply industry, conducting municipal composting and brush management projects across the New England region. He obtained his BS degree in soil and water sciences from the University of Maine, and while he's had many opportunities to work all over New England, he sincerely enjoys working for New Hampshire DES and helping protect human health and the environment. So with that, we will take it over, Anthony. Oh, I don't hear your voice, Anthony. I don't know if you're muted.
I am unmuted now.
Okay, there you go. Go ahead.
Thank you, Jennifer. As Jennifer introduced myself, I am Anthony Druin. I am the administrator of the Residuals Management Section. We are in the Water Division of the New Hampshire Department of Environmental Services. And I thank you for joining me today. And we're going to discuss our PFAS biosolid sampling out in the field and cross-contamination issues we faced and things we look at while we're out there conducting our investigations. So today I'm going to do a quick overview of our residuals management section here at DES. As well, we're going to delve into our sludge management rules, and specifically we're going to just talk about the sludge quality certification program. As well, we're going to dig into our SQC PFAS investigation. We're going to talk about the NEIWPCC and NEBRA sampling guidances that we follow here in New Hampshire. As well, we're going to talk about the quality of sample equipment cleaning and the sampling events themselves. And then we're going to review our 2017 through 2019 SQC PFAS data. Pretty quick review, nothing too in-depth, but I just wanted to show you some of the results that we've been getting. So our residuals management section here at DES, again, we are within the water division and within the wastewater engineering bureau. We're a small section. I'm the administrator. We have a permitting and enforcement engineer. Her name is Judy Sears Houston. Currently, our sludge and septage coordinator position is vacant. We'll be looking to fill that in the coming future. And then Timothy Sweat is our inspector. And all of these roles have functions. Most roles have a permitting function, except for the sludge and septage coordinator, where there's a lot of training and outreach with that role. So the rules and laws that we apply sludge management or residuals management in New Hampshire are pretty simple. Our land application rules are ENVWQ 800, and our septage management rules are ENVWQ 1600. Those all operate under the law RSA 45A that allows for land application of biosolids in New Hampshire and septage. For the landfill disposal, we have ENV SW 100 to 2100, and the law there is RSA 149M. Our solid waste division works with the landfills that are permitted within their programs that accept sludge. So our section doesn't really deal much with the landfilling of sludge or the reporting and record keeping, but we do work with the solid waste division on projects and things like that. Incineration is ENV A 600 and the federal code 40 part 60 subpart O. We have one incinerator in New Hampshire, that is the Manchester wastewater treatment facility. They incinerate their sludge, and the ash is then managed out in the marketplace. And then we have our federal regulations, which we follow, which is the 40 CFR Part 503. Those are your the EPA regulations for biosolid land application and recycling. So here for New Hampshire in our residuals management section, we have for sludge and septage management, we're looking at hauling, residuals quality, sites for land application, the facilities that are processing the material, and of course, record keeping and the reporting to us here at DES. To delve into a little bit of the sludge quality certification, so this is the part of ENVWQ 800 where we are looking at permitting the generator of the biosolids or sludge. And this is in order to distribute bulk biosolids or sludge in New Hampshire, you must obtain a SQC through our section. And within that certification, when you are filling out that application, we're looking for, and this is written within our rules of WQ 809, we're looking for basic information, the industrial pre-treatment information, the quantity that's generated. We're also going to be we're looking into the pathogen and vector attraction reduction options that that facility is following. And I just wanted to quickly go over the difference. So with biosolid processing and pathogen reduction, we have Class A and Class B biosolids. Sometimes you might hear out in the marketplace, process to significantly reduce pathogens. That is a one-step process that will generate a Class B biosolids. Another term you might hear out in the marketplace is process to further reduce pathogens. That typically is a two-step process, which is going to generate a Class A biosolids. A Class A biosolids is going to have less pathogen content than a Class B biosolids. And the acronyms you'll hear is PSRP and PFRP, and I've highlighted those in red. So I just want to note that just in case you were a little confused on what biosolids are and what is a Class A versus a Class B. And those vector attraction pathogen reduction requirements come from the EPA 503 regulations I was just talking about. As well, we in our program here for sludge quality certification, we also regulate short paper fiber that is beneficially utilized and drinking water residuals, which are also called hydrosolids. So from a drinking water treatment plant, those residuals can be blended into soils for beneficial use. We're also looking for historical and current quality data. So within the program, when you have a certificate, there's annual testing. The frequency is based on your dry volume output. You're obviously record keeping all of that data and information and reporting back to us every January of the previous year. That last business day of January is when it's due. And you have to renew your certificate every 5 years. If you are not a public entity, there is a fee to obtain an SQC. And then every year with that annual report, you are to submit a $500 fee to DES for our testing program, where we go out and third-party test the program. So to get into a little bit of the sludge quality certification, I just want to note what beneficial use is. If you hear this term out there, beneficial use is the utilization of the nutrients and organic matter from the biosolids for the agronomic need, as long as it does not pose a significant threat to human health or the environment. So beneficial use applies to agricultural practices, forest, land reclamation management practices. This is not the exact definition in the New Hampshire rules, but this is pretty much in a short abbreviated version. So what we're looking at here is taking this material, utilizing it for its nutrients and organic matter, and beneficially utilizing it to create a vegetated area. So again, bulk biosolids must obtain that SQC to distribute in New Hampshire. And that annual soil test that the sites are going to go under will determine that crop nutrient demand that is going to be supplied from the biosolids. And we actually, within our rules, have a UNH, University of New Hampshire, BMP that residual managers must follow when they're land applied biosolids in New Hampshire. Class B land application must obtain a site permit through our section, which is a pretty strict process, a lot of public notification, and information has to be shared with those sites. And as for our SQC program, we do have concentration limits and screening standards for VOC, SVOC, PCBs, dioxin, and metals, a total of 168 analytes. With PFAS included, we require 177 analytes to be screened annually. Currently, we are working on that PFAS soil leaching standard, which will give us a screening standard. But as of right now, we have 168 in the program. So just some quick pictures. Here's a before and after of a land reclamation site, so you can see that beneficial use happening there. This is a landfill cap job where the biosolids are utilized to create a vegetative layer on top of that landfill, obviously to prevent erosion and create stability in the slopes. And then here is a classic agricultural setting. This is corn silage, or corn being grown for feed purposes. This is a Class B site, so you can see the before and then after that corn being grown. So great examples of beneficial use being done here in New Hampshire. So how did we get to requiring PFAS testing in our biosolid program? There was a bunch of events that were occurring across the country and specifically within our state and region that were raising awareness of PFAS and contamination issues in groundwater and drinking water. So we went out and started to investigate PFAS concentrations within our biosolid program and beginning outside of our biosolid program, sludge in general. So our former administrator, Ray Gordon, this was before I came on to the department. Ray had gone out in the field and following sample guidance that we'll go over in a second, he was able to go out and gather some information and generate some sample and some facility inspection reports. Specifically, he visited 12 SQC and non-SQC permittee holders. Sampled was conducted by Ray himself. We used a couple labs to analyze this material. We are contracted every 2 years with a successful bidder. Class A and Class B biosolids, wastewater treatment, sludge that has not been treated to be a biosolids, short paper fiber, from paper mills was sampled. So 9 compounds was analyzed initially. And what we found is in the percent detections here, you can see that we were finding these compounds in these sample investigations. You'll notice there that there's a PFOS max of 390. That was one sample. And in fact, it's the sample you see that picture of. That is not a biosolid sludge. That is a sludge that is to be landfilled. but that material, we wanted to see where that was, and we got some high numbers. But nonetheless, we did start detecting that. So again, 2018, we went back out and we sampled 16 sludge quality certificate holders, again, conducted by the same person, Ray, that person in that picture. This time we only used one lab, Test America, and we sampled all the generators within our program, and again, just looked at those 9 compounds analyzed. Found it again. You can see PFOS 93.8%. So that definitely raised awareness on our end. And we, at that point, needed to implement a screening for PFAS and really looking at the 4 compounds that New Hampshire is regulating or looking to regulate here in the near future for drinking water MCLs and AGQS, PFOA, PFOS, PFNA, and PFHXS. But we decided that we wanted 9 compounds analyzed per year, and that list may grow. But for right now, we're requesting 9 from them. So in order to do that, we couldn't. We didn't revise our rules, but we revised everybody's sludge quality certificate right there on the right. And also we offered a training for everybody. We did a group training where we brought all of our SQC generators in and we talked about sampling and analysis for PFAS. We brought in NEBRA and former specialists from the industry to talk about sampling and analysis and the importance of the SOP, which we're about to discuss here in a second. And then as well, I went out at this point and sampled every single generator in 2019. And doing that, we paid for the sampling for the generators and also trained them individually for what is needed using this NEBRA guidance we're about to go over. We felt the need to do this because we were just instantly putting this requirement on them. There's still a lot of unknowns right now currently with sludge analysis of PFAS. Jim, the next presenter, will talk about isotope dilution, but currently we do not have an approved test method for sludge analysis for PFAS. And as well, the knowledge and information that the operators had at the time, they needed to be trained and better understand what they're doing when they're sampling for this so that cross-contamination issues are not to occur. So what is the guidance that we are training people on? First, initially, within our rules and regulations, there is a NEIWPCC sample guidance or sampling plan guide that we have implemented in our rules that the SQC holders must follow to implement a sampling analysis plan that follows their certificate with us so that they are properly analyzing their biosolids for what they are required to. On top of that, this NEBRA guidance that came out. So NEBRA is the Northeast Biosolid Residuals Association. They're a high active player in the residuals management world and in the industry. We go to their conference every year and we keep up with them and obviously educate them and inform them on what's latest and greatest with New Hampshire and the regulations. And they are working closely with all the industry end users and stakeholders on education outreach and obviously making sure that they know what's coming down the pipeline for them. This guidance was written by Michael Rainey. Just a side note, Michael Rainey is a former administrator of the section that I administer now. I have a high respect for Michael, and this document was very well written by him, and you can see that it was peer reviewed. A couple things, I know this slide is a little busy, but within this documentation, there's an appendix D1 that really goes over some good stuff, talks about the personal care products you need to stay away from and things that you can wear, clothing that you need to stay away from, and stuff you can wear, and documentation all the way down to those notebooks that we were using out in the field to prevent when it was raining. Those are coated in PFAS. So those are certain things you need to keep an eye out for. The dish detergent or the lab detergent you're using to clean your equipment is very important. You want to make sure that's PFAS free. We use Liquinox, which we'll go over in just a second. And you just want to obviously take a look at this sample guidance if you're going to be sampling biosolids and sludge. It's worked very well for us here at DES, and I think it's going to do well for our generators and permittees. They have a great equipment checklist. I've created my own that is something that every sampler should be reviewing before and the day before they're going out and sampling, so that they're making sure that what they have, they're ready to sample for PFAS and are aware of these detection limits. We're not looking at parts per million anymore. We're looking at parts per billion or even parts per trillion. So, they need to be aware of the potential for cross-contamination while they're sampling. So here's a lovely picture of me I went out sampling recently, and during the pandemic here, I was to make sure that we were keeping our distance. So you can see I have my mask on there. It's 100% cotton, had to make sure of that. But when I'm out sampling biosolids and sludge for PFAS, a couple things. I want to make sure I'm wearing my PVC boots. As well, I have my nitrile gloves on. I have my proper eye protection, and obviously right now in our current times, my proper face mask protection. And key, everything here is on my clothes is 100% cotton. Another thing that I do to help prevent myself from cross-contaminating the sample is I hold off on the shower the morning of. I don't have any detergents, lotions, shaving cream, none of that. I put my clothes on, I come into work, and I worry about that hygiene practice after the sampling event. But at least from that, I can be comfortable knowing that I didn't put any detergents or any lotions on me that have potentially PFAS in them and could cross-contaminate this sample. So I just want to go over an example of a cleaning. This is my bucket and sample probe after a cleaning of a short paper fiber at a paper mill. And you can see that there is a residual film in the bucket and on the probe, and there's residual still in there from the sampling event. And that needs to be removed, and we need to make sure that's clean for my next sampling event. So what is that SOP? I extracted this out of that NEBRA guidance. I kind of simplified mine a little bit. I don't use methanol in my cleaning steps process. I don't think it's needed, and it's a little bit dangerous out there in the field to be handling methanol. For risk of yourself and then risk of the environment. But so I've stayed away from that. But really the key thing is you got to get that equipment rinsed off. You got to remove the solids off the equipment using a brush that obviously is not coated in PFAS and PFAS-free lab detergent. I use Liquinox soap, and I'll show you a picture of that in a second. And you really don't need a lot of Liquinox soap. I use a capful, and if you'll see the cap on this container, it's a very small amount in order to clean my equipment. So I'm not, really soaking this material in soap in that manner. After scrubbing the material and removing all those solids, we're going to get that, all that soap off of there with that tap water. And then after that step, we want to make sure we get a triple rinse using PFAS-free deionized water, and make sure that's a PFAS-free. Triple rinse and remove. And then I store my containers and my buckets in a dry, clean area. I don't wrap my containers in tin foil. I don't wrap them in anything. I just keep them in a dry, safe area. The key thing is when I get to my sample site, I do another triple rinse right there. And even at that, I've done equipment blank rinsates off of that triple rinse to make sure that there isn't cross-contamination from that car ride from my sample storage location to that generator. Key thing is those equipment blank rinsate samples to double check if your cleaning process has done right. And we'll go over that now. So Liquinox soap is the soap I use. And if you can see this kind of bottle, that cap is very small, so you don't need a lot of this material. And then that's post cleaning. So, this is post triple rinse. So if we kind of go back here, you can see that was the dirty bucket and probe, and then we get over here, and that's my clean bucket and probe. And then, I would take this to a generator and triple rinse. So how do I know this works? Well, on 11/21 last year, I did an equipment blank rinsate from cleaning out in the field. So I sampled a manufactured topsoil out in the field. I did the cleaning from the back of my vehicle with the permittees with me right there. I cleaned the material on that third DI rinse. I collected that. And then I went and sampled, another biosolid sample. So that first biosolid sample detected 14 compounds, and my second biosolid sample detected 6 compounds. But the key thing is my equipment blank yielded less than 2.36 nanograms per liter for all compounds analyzed. The field blank from that same sampling event, and I'll show you a picture of that, yielded less than 1.87 nanograms per liter. So I took this field blank right in front of the stockpile, right in front of me to see if anything was shedding off of me at that moment, or even, coming off of the pile itself. I've had a couple of these events where I have taken a sludge sample that is quite higher than others in the program, and then clean the equipment at the permittee's lab at their wastewater plant, done my triple rinse with my DI water, transported the sample equipment to another generator, sampled, and this specific example on June 1st was a short paper fiber material from a paper mill, and that second sample from the paper mill showed less than 1.11 nanograms per gram for all compounds. So what is this saying? This is saying, you know, we had 10 compounds detected in one sample. I cleaned everything, went and sampled the next sample, and I got less than 1.11 nanograms per gram for all 24 compounds. Just had 2 more reports come in literally 15 minutes ago that proved the same thing again. So I'm really confident and comfortable with this NEBRA guidance and the sampling steps that Mike and team have written. And I highly suggest, you know, looking at that and following that. So here's an example of the field blank that was taken. That's me. There's me on the left taking the field blank, and then me on the right there after I ball it up. I don't know what the question look on my face is, but just to show you the order of these samples that were taken. So the manufactured topsoil was taken first, equipment was cleaned, then that triple rinse, you had the equipment blank, and then biosolids were sampled, composted biosolids, and then from there I did the field blank as this picture you just see here. So it's really important to understand when you're out there sampling biosolids, what you're looking at and what potentially could be cross-contaminating the sample. Biosolids come in many different forms, many different processes to treat them. So you need to be aware of that process and step and what you're sampling and what could be causing cross-contamination. This first example, I had to sit inside this roll-off can and collect biosolids as it fell down into this pile, because when I got there, the initial sample port location was right next to the dewatering unit, and it was using this plastic sample collector that I just questioned, and I didn't know if PFAS wasn't containing it. So I said, you know what, I'm going to eliminate that step and I'm going to do it this way. Some people would be grossed out by it, but I didn't get hit by any sludge at all, and I was able to confidently take a sample. Sometimes when you show up to a wastewater plant and you're expecting to have a uniform load across the trailer, you don't. You end up having multiple different layers. This material is going to a compost facility, not to land application. And you got to take a look at this and wonder, you know, what am I sampling and how am I going to sample it? So I was able to, you know, understand, you know, the volume between the two piles there and grab a collective sample that was going to best represent the trailer as a whole so that we could see what was being delivered to that site and those PFAS concentrations. Other times you show up and the generator has the windrows laid out in 1,200 yard windrows and everything's perfect and easy, and you know, this is very clean and nothing to worry about. You know, it's a pretty simple job. So sometimes you come up and you want to make sure you're measuring these piles to get that volume and that amount, so you can get the proper amount of grab samples to make up a composite sample. For me, a 1,200 yard windrow like this, I'm taking 25 grab samples, maybe up to 30 grab samples if I find that, you know, there could be, you know, an area that I'd want to avoid that could look differently, or however, you know, random samples are random samples, so you should be grabbing no matter what. But typically 1,200 yards, 25 to 30 samples. And then we also have, this is a anaerobically digested biosolids off of a screw auger press. So, you know, you have to look at how am I sampling this? I'm getting my sample probe in there, and I want to be able to extract that sample out the best way without hitting anything and making it so that there isn't any potential cross-contamination issues. As well, you show up to a site like this. This is a composted biosolids using wood ash, alkaline stabilization. And you need to be able to make sure you can get in and out of these windrows so you can collect that randomized sample and get the best representation of what you're looking at. When you, this is a short paper fiber sample, so we want to make sure that, you know, how we're sampling this, you know, we're not having any issues or any other cross contaminations coming in, and making sure that the biosolids or sludge falling down isn't going to rain on you, and you're aware of that. And your potential cross contamination is not going to contaminate this pile as you sample it. Very important. Pulling off a press, this is a belt filter press. You have material that's coming off and sheets. You know, you want to be able to make sure you're grabbing that sample properly, getting that into the sample container, and getting the best representation you possibly can. And you know, sometimes with this, you're going to want to grab it with both hands, or maybe not grab it with both utensils, or however you're going to get this off into the sample container. And you just want to make sure you're aware of how much you're handling the sample and having potential cross-contamination issues. This is drinking water residuals. If you've never seen it, this comes from a drinking water plant. So when obviously when they're treating drinking water, there is a residual matter from that filter bed treatment. And so you know, when you're going in there, you want to be able to make sure you're going in and grabbing that sample best. You know, have your PVC boots are key in these moments, because you're obviously walking into the material, and you could create cross-contamination there. So down to the really the nit and gritty here, what I think people want to see is, you know, what are the results? What are we seeing in New Hampshire? And what I've given you is the 2017 through 2019 sample events. I did combine 2017 and 2018 together because certain SQC holders were done 1 year and certain were done another year. I did take out all the non-SQC holders from those 2 years, so that we are looking at a direct comparison of the beneficially utilized biosolids in New Hampshire. And some of these generators are from out of state. They're not all New Hampshire based generators. So even if you are an out of state generator, you got to get that permit through our program. So you can see here, this is the sum of the 4 compounds regulated in New Hampshire, or soon to be regulated, for PFOA, PFOS, PFHXS, and PFNA. And the units is nanograms per gram, parts per billion. Notice on the bottom there, samples analyzed for PFAS were analyzed using isotope dilution. Jim will touch on that in the next presentation. And within the QA/QC report, I just want to note that you know, there were compounds, and some reports a lot of compounds, some not so much, were flagged for being outside of percent recovery acceptable criteria. So it really, you know, when you look at the data across the board, you can see reporting limits, you know, here and there, and not, you know, uniform, and as well with the flags of being out of that criteria. You know, it does raise questions for, you know, how accurate is the data, and that's obviously what we're doing with this investigation. We're building understanding and building data. We want to see what's out there so we can begin to work on regulations. Right now in New Hampshire, we're about to begin the USGS soil leaching study. That is going to be crucial and for us to determine a sludge standard for the biosolid program that will be implemented once that study is done. So, you know, when we're working, and obviously the approved test method is going to be key on implementing this screening and the amount of screening in our rules. So all of these things are ongoing and evolving, and we are, you know, continually working with our generators to protect, you know, human health and the environment. I think that's so important. So with that, that's pretty much my presentation. So I will leave it up for questions.
Great. Well, thank you very much, Anthony. And we have a few questions that have come in, so let me get right to them. Someone was wondering, and so was I, about the equipment blanks that you did, and you had 2 different levels of PFAS that were found. They were very small, but they were different, and shouldn't, in theory, they be 0, but you know, why is it okay that they were different?
Okay, so key point there with, for sure. So on November 21st, there I have the slide up. One was an equipment blank and one was a field blank. So you'll get the 2 detection limits because maybe there were some interferences there where you can't get the same level as maybe that field blank. The nature of the equipment blank, it is that last rinse of deionized water that is then collected into a PFAS-free water sample container. The field blank is water, DI water supplied by the lab. I have 2 containers, and I'm just transferring that fluid into the other container and capping it. That's how the field blank is collected. So, you know, essentially that equipment blank may have a higher RL there due to it may have just a little bit more interferences in there and causing that. So that's why you see those 2 RLs, and hopefully that explains the differences between those 2 samples.
Okay, well, and then there's the June 1st.
The June 1st, there was not an equipment blank there. What I am showcasing is that I took a sludge sample where I had 10 compounds detected And for the 4 compounds in New Hampshire, it was quite high or higher than others where we're above 50 parts per billion. I then, after that sampling, I cleaned all the equipment in the lab, literally just transported to the next generator, rinsed the equipment off, and then took a sample. And what I'm showing there is that short paper fiber sample taken in the PM has a detection limit of less than 1.11 parts per billion for all 24 compounds, which is like some of the lowest RLs we can get for sludge. So what I'm showing is that the cleaning, we didn't see any cross-contamination from that previous sample come across. Does that make sense?
Yes. Okay, thanks for the clarification. Someone is wondering how many grab samples would you take off a belt filter press?
Oh, great. I actually didn't bring that up. And so in that NEIWPCC guidance that I brought up, see if I can bring it back here just to show you. So this guidance document right here, the NEIWPCC guidance, within that document, we educate our generators to take a sample every 5 minutes for 40 minutes. So you end up taking a total of 8 samples. I have some generators out there that they'll go out and they'll take samples for, an hour, 2 hours to get a better composite. I think with PFAS, you want to be aware of, if you're taking that sample and then you're taking that bucket and that sample collector and putting it off to the side to an area, you don't want to put it in an area that could have dust from the environment cross-contaminate the sample. So, the longer the sample sits in an area that could be exposed to cross-contamination without being put into that sample container that's going to be analyzed can be a risk. So 40 minutes every 5 minutes.
Okay. Now we're going to switch to the very last slide that you were talking about. And do you have any thoughts on why the 2019 PFAS results were consistently lower than the earlier ones?
Well, my hope is people are using less of it in society. Biosolids and sludge mirror our, daily use of chemicals. So, when we analyze wastewater, we analyze sludge, we're seeing what people are putting down the toilet and what are people washing down the drain. So if we are seeing this reduction, now keep in mind this is parts per billion. So, with class A biosolids, you're looking at 22 to 18, 19 parts per billion. How big of a difference is that? Not sure yet. I need more data. So yes, we are seeing reductions, and I am, so the 2020 data, which I didn't put up here, the sludge went up. So, it didn't decrease like you see there. Hydrosolids stayed the exact same. Paper fiber pretty much reduced a little bit, and the other B and A biosolids reduced slightly. But so I think, we're seeing in general biosolids from a wastewater plant, we're in that range of 10 to 20 part per billion. Paper fiber in New England is definitely on the lower end. A lot of these paper mills have procurement programs for the recycled feedstock they're taking in. So they're doing a great job on monitoring the PFAS coming into the paper mill. Wastewater plants, they're conveying PFAS. The public and industry are disposing PFAS into the wastewater stream, and the wastewater plant is just conveying it as it passes through. Wastewater plants weren't designed to treat PFAS, so but paper mills have a better control of that with their procurement programs.
Okay. Do you have any experience with sampling the water, not the sludge, and cross-contamination?
So for sampling water, I do not have, for PFAS sampling, I don't have any experience yet. For PFAS sampling, I've only done solids. I do sample septage, but that's not water, and the septage, we take that as sampling sludge. We do have the Drinking Water Groundwater Bureau, so if need be, we can always share the information of that group and the people that can educate on that end.
Okay, another water-related question, which is just about getting the PFAS-free water. Do you get it from the lab or where?
So when you're our lab here, they're making their own DI water and testing for it. But when you're getting any type of DI water, if most our smaller plants in New Hampshire, they'll buy cases of bottled DI water or distilled water for their cleaning purposes. So you just want to make sure the vendor you're talking to testing, analyzing for it, and if they are and they're detecting it, what are they doing to treat for it? You know, to show that it is a PFAS-free deionized water.
Okay, now we're going to have to wrap this up in a minute, and we're getting more and more questions. But how about detection limits? What do you have a specification for detection limits for biosolids that you need?
Right now, we are still generating data. I'm not ready to sit here and say this is the detection limit. On average for biosolid sludge, I'm seeing 1 to 2 part per billion. As a RL, but there are times where I get some samples that are higher than that. I had a sample this spring that had a RL of 39.4 part per billion, didn't show anything, and it was an anaerobically digested biosolids. So, but for RLs, no, I'm just still collecting data. When the approved test method is approved, EPA approved, then we're going to move forward on implementing the screening and analysis into our rules and regulations, and from there we'll have MDLs set up like we do with our other compounds.
Yes. Okay. Well, here's several people have asked a similar question, which is about the levels of other PFAS besides the 4 that New Hampshire is focusing on, and are there trends with those over? I guess you're only analyzing for 9, or cause some people are doing 21 or 23, or I don't know what the. So, yeah. But there's definitely an interest in what's going on with other PFAS.
So we asked for 9 compounds to be screened every year within the certificate. We, as an agency, with our contract with the lab that we have today, Alpha Analytical, we are analyzing for 24 compounds. So 2019 and 2020 sampling events, we're analyzing for those 24 compounds. Another thing I did not note, I did all the sampling for 2019 and 2020. I continued to go out and do the sample investigation for the permittees because I wanted to keep the sampler to one person, keep it to one lab, and obviously continue to have the conversation if I could. This year it was harder because of social distancing, but just try to keep congruency from year to year currently while we are still investigating and looking into setting regulations, so we can get a stronger or more accurate idea of where these concentrations are. And so for the compounds that I'm seeing, we do see other compounds. There are precursors that come in detectable on multiple samples. PFHXA is another small chain compound that we see in our detections. And you can kind of see here, if I go back to the 2018 slide, sorry, I'm making you guys dizzy. So here you can see, we do find detections either 50% or more in a lot of these compounds of these 9. As for the other compounds out of the 9, from the 9 to 24, those precursors we are detecting, but for these, a lot of the detections are these 9 compounds.
Okay, I'm going to do 2 more questions and then we're going to switch over. So there's some confusion about composite samples and grab samples. There was is it recommended you do single grab samples, or I'm not sure. It just confusion.
Yeah, so that is kind of a question from some people out in the industry, is what's the safest thing to do when sampling PFAS in a sludge or biosolids, because if there's all this potential cross-contamination that can happen, taking multiple samples obviously increases that potential for cross-contamination. But there's also the factor that you want to make sure that you're getting the best representation of that stockpile or that production of that day. So a composite sample, in my opinion, is better than a grab sample, but that is still being argued amongst scientists in the industry. I think if you are to properly take the sample and follow strict guidance and make sure that you are doing all the proper steps to prevent cross-contamination, a composite sample is going to give you the best result. You could happen to, in one grab sample, just grab a little pocket that could be higher concentration than really what's representing that whole stockpile. And if that's the number that's going to represent your biosolids, you know, that could make or break where you're going to manage that material and essentially either cost you or not cost you a lot of money.
Okay, actually, I'm going to ask 2 more questions. So one is just, do you do anything in your vehicle to prevent cross-contamination or particulate or anything on
So
the equipment?
I keep the back as clean as I can. I mean, I'm sampling sludge. It's not a clean job. But what I've found, and that's why I was, you know, kind of doing the equipment blank rinse sites, obviously, and looking at the cleaning and how important it was. I was hesitant, you know, people in the past were wrapping the equipment in the vehicle with certain things. And I was like, have you tested that for PFAS? And I wasn't getting, you know, no, I haven't, or, you know, I don't know. So for me, I keep the equipment, I don't store it. I try to keep it off the seats, or, you know, if you don't know if your car seat's been treated for PFAS, it's a big thing to treat it for. I keep it in the back on, we have this PVC like kind of liner that's on the back of the car. And all my cleaning, my DI water is right there. So it's just a matter of the rinsing after I transport it. So no, I really don't take in special cleaning. I've thought about building like a pine box and storing it in a pine box. But I haven't had any data that's saying that's, you know, I should be doing that. So until I see something that's like, okay, now I'm having issues with that, then I would do that. But
And you are doing the equipment blank before you start, it sounds like.
Yes, I can't do it all the time because I only have so much funding. And where, you know, we are investigating right now, we don't have sludge limits, we don't have soil numbers or soil standards. So I take this as an investigation and gathering information and gathering understanding of the SOP and what's the best way to take these samples while we are working on that analytical method.
Okay, now as a segue over to our next presentation, what analytical methods are you using again?
Yes, so I kind of put it, and you'll see it in the slide when Jennifer shares it. On the bottom there, samples were analyzed using isotope dilution, and I'm pretty sure Jim will cover that on the next presentation. But our contract currently is with Alpha Analytical. They won the bid in 2019. Our section shares a lab contract with our Hazardous Waste Remediation Bureau because we do very similar testing. So that was big for us, and the bid was what type of method and what is your QA QC practices in the lab, and Alpha is conducting those.
A modified 537.1, is that what it is?
You know, some people don't like to call it that. You know, lab people will say that's not the right way in identifying the method in the lab for analyzing sludge. So I always just say isotope dilution, because it can be a little confusing.
All right, well, in the interest of time, we're going to have to forego the rest of the questions, although some of them I think will be addressed in Jim's presentation. So we're going to move over. So thank you so much, Anthony. That was a lot of good information. And again, these presentations will be posted, PDFs of them, on the NEMOA website after the webinar, either later today or tomorrow. So I'm going to move the presenter over to Jim Accolini. He is the Vice President with Alpha Analytical, and he serves as the practice leader for the Laboratory Specialty Analytical Service, which PFAS certainly is the specialty. Jim has over 40 years of environmental analytical and consulting experience working on a wide range. Oh, now I just lost him. There he is. Wide range of different projects. He's very active with a number of regulatory work groups and industry associations where he has given numerous technical presentations and training programs, of which this is one. So with that, welcome, Jim.
Thank you, Jennifer, and thank you all for attending the webinar. So I'm going to divide my time today. PFAS is really a moving target, certainly as far as from the environmental perspective goes. So I'm going to spend the first half of my time talking about analytical methods and where we are today. And then the second half, I'm going to share with you the results of a cross-contamination study that we did in conjunction with TRC. So this all started in 2009 with method 537. And this is an analytical method that was developed for the analysis of drinking water. And it was conducted, developed in time for the UCMR 3 program. And it really was different than most of the other procedures that people may be accustomed with from an environmental analysis point of view. It used solid phase extraction, which was pretty widespread use in drinking water, but not so much in any other type of environmental media. And then it also used LC tandem mass spectroscopy. And that, again, that instrument is different than most environmental labs were familiar with at the time. So this came out in 2009, and again, drinking water method. In 2018, this method was updated, and there are 537.1 revision. The original method had 14 target compounds. This one now has 18, and they added, the 4 that they added are all considered PFAS replacement compounds, as the C8 compounds, the PFOA, the PFAS, those were all voluntarily removed, or people trying to move away from that, and generally a shift to maybe shorter chain compounds or just ones with less of an environmental footprint. So these 4 that they added are considered replacement compounds. Now, the one replacement compound that probably generated the most press coverage is GenX. And as you can see, it's not listed here, but that's because GenX is the ammonium salt of this hexafluoropropylene compound, the first one. And so in water, it's an anion, and we're looking for this dimer acid. So this is the target compound on 537.1, but it is GenX. So just in the end last year, EPA released method 533. And now this is another drinking water method for PFAS. However, there are some significant differences. And the first difference that I really wanted to point out to you is the different target list. So as part of this, when the release of this method, they definitely were focusing on shorter chain compounds, and 537.1 was limited in just which compounds were amenable to that procedure. So they extended the list. 537.1 had 18 compounds, and 533 has 25. However, as you can see, they're mutually exclusive here, in that there are two different compound lists. And if you wanted to analyze a drinking water sample and use an EPA certified method, and you wanted to get the most number of compounds, you would use both of these together on the sample, and you could look for up to 29 compounds this way. So there are some other important differences between these two procedures, other than the compound list. So the first one is 533 is an isotope dilution approach, and it uses extracted internal standards. And I'm going to talk about that in a minute as far as what that means, but that is a very significant difference between 533 and 537.1. The other one is it uses a different solid phase extraction compound. This is the weak anion exchange cartridge, and 537 used a dibenzene cartridge. And that difference in cartridge is what makes 533 perform better for these shorter chain compounds. So both of those changes were significant in making, in my own personal opinion anyway, 533 is a better method. There are a couple of other changes too. 537.1 used Trisma as a preservative, mostly as a chlorine, I'm losing my mind here, a chlorine dechlorinating agent is what I was trying to say, I'm sorry. But it also acts as a buffer. And 533 uses ammonium acetate in its place. The other significant difference is a change in holding time. 533 uses a 28-day holding time versus the 14 of 537.1. So isotope dilution, it adds a lot of additional certainty to the analysis. And the reason for that is that these internal standards are added at the beginning of the process. So before the sample is extracted, put through that solid phase extraction cartridge, these standards are added and they are carried through the entire process. So any performance issues, any biases, matrix effects that are going to affect the analytes in the sample are also going to be, that effect is going to be seen with these internal standards, and it allows the laboratory to then normalize for these differences. So now about these extracted internal standards, they are labeled compounds. So they're primarily carbon-13 compounds, but some of them use deuterium. And so they're an exact, chemically identical to the analytes that we're looking for. However, they are labeled, and when you're using a mass spectrometer, you can tell the difference between C13 and C12, and that's how they're separated instrumentally. And it allows us to then do that correction. And I say it's a compound-specific internal standard in that for each compound you have a label standard that you can use. However, the reason for the asterisk is they are not always available. So for, I think the longest list that we do is 36 compounds, and we do not have labeled compounds that we can use for all 36. There's a limited number, and that's something in the PFAS analytical world that is always an issue of trying to get new standards, either for compounds as direct, calibration standards, or in the case of internal standards, the labeled compounds. So as you can see, carrying this through the whole process, you can really get a good result, and definitely increases the certainty of the analysis all around. So these two methods are drinking water methods. Now, what if you have a different type of matrix, a wastewater, or going to soils and biosolids, for example? That's definitely a different type of sample right from the get-go, and there's going to be some significant modifications that are going to be needed. The other thing is, depending on your compound list, what if there are compounds that you are interested in that are not on these two lists? You're going to have to do something differently. So people do refer to, a modified 537 or 533. EPA does discourage that. These are drinking water methods that are used for compliance. They're used for things like the UCMR, where the data is compared nationwide. And if laboratories were modifying these methods individually, maybe that's the comparability of a program like that would become in doubt. So the EPA is very concerned about not letting that happen. So what laboratories have done in these cases, as we have done, other laboratories have done, is they develop their own proprietary method. And these will still use liquid chromatography, tandem MS. However, they may use a different solid phase extraction cartridge, or they may use multiple ones, depending on what compounds they're trying to determine. And for the most part, most of these methods that are in-house methods, if you will, all use isotope dilution. I know that's what our method does. We use isotope dilution as well, and we use the wax cartridge that is similar to method 533. So when you're moving on to other matrices, there is, obviously some additional prep that needs to be done. And so people will ask me about filtering. If you're sampling a groundwater, for example, it will silt in it. And filtering is not a good idea because the cartridge itself that it's used for filtering may actually absorb some PFAS compounds, and that would lead to a low bias. And then in another case, potentially a plastic housing or material the filter is made of could potentially actually leach PFAS into the sample. So for both reasons, filtering is not a good idea. However, if you have a sample that looks like that, that's not going to make it through that solid phase extraction cartridge. And what we would do, and what typically is done, is we would centrifuge the sample. And another important consideration when doing that, you're separating the sample into essentially a liquid and a solid. You have to make sure that you extract both and then recombine that extract in order to get a representative analysis. And this is where something like isotope dilution really comes into play, because you're adding those spikes, those label spikes, well before any centrifugation or any other handling. And so you're getting a true picture of what the performance is. So when you go to soils and biosolids, there's even more prep, as you might imagine. Now there is essentially an extraction that needs to be done, and you would certainly use isotope dilution up front to carry through the whole process. There is a solid phase extraction cleanup cartridge that we employ as well to try and essentially remove any interferences before it gets to the instrument. Now with biosolids, as Anthony has talked about, biosolids present a pretty significant challenge to the analysis in that, one, they have a high carbon content, obviously, and so that can be that can be an interferent. It can co-extract materials, and it is something that you do need to deal with, and using something like a cleanup cartridge can help with that. The other factor with biosolids is the percent moisture. These samples are very, very wet, so we're reporting on a dry weight basis. So what that tends to do, this high moisture content, will drive up detection limits. And so when you look at some of these screening levels for biosolids, they are low in consideration of the fact of the dry weight basis point of view. And so that is a challenge to clean up the organic material and get enough dry weight to be able to report a solid detection limit. Then as you extrapolate further to other matrices, and I'm talking briefly about tissues here with vegetative matter, fish, shellfish, we've done a lot of these. And what we found is actually each type of sample, even to the species, has its own specific matrix, if you will. And so we adopt our cleanups and prep methods accordingly to try to maximize performance depending on which type of sample it is. And in an extreme case like this, where this was a waste stream study from a landfill, what was sampled is this pile here on the left. And so there was a lot of discussion between us and the field team in how to collect a representative sample, what we need to see on our end. And as you also might imagine, a lot of method development on our end to make sure that the approach we followed was as representative as possible as what was in that container. And again, isotope dilution was key here as well. So EPA last year, at the end of the year, came out with method 8327. So it was an aqueous method, but essentially a non-potable water method. And it uses liquid chromatography, tandem MS, but it does not use solid phase extraction. It's a direct aqueous injection method. And this procedure really wasn't well received, I guess I would say, in the environmental community. There are some things with it. Uses external standard calibration, for example, and the detection limits were a little bit higher, and to the point where the DoD had come out and essentially said that they considered this procedure a screening method. So again, not widely used. And there are a couple other methods that people are looking forward to seeing. And the first one was 8328, and it's been discussed for a while, and not sure exactly what the status is on 8328. However, this method is non-potable water, but also soils and sediments and biosolids. And this was, again, same instrumentation. It's going to use solid phase extraction. Was an isotope dilution method as well. And at the time, it was considered to be looking for 24 analytes plus that Gen X compound. And the other thing that was pretty neat about this is that the DoD, as you well imagine, being a significant, a lot of interest with PFAS on their sites. And so they have the Quality Systems Manual, which for any environmental analysis that's done on a DoD site has to be, you have to be DoD certified and you have to follow the QSM. So given the fact that once you get off of drinking water, there's not a lot of standardized methodology there, they were very specific in putting together essentially a table of method performance and QA/QC requirements that you would essentially overlay over on top of your PFAS method. And so 8328 was supposed to be developed in conjunction with the DoD. And so there'd be essentially one benchmark, which I think is always a good idea. Now that method is still not sure exactly what the status of that method is. So at the same time, there's another group, and I'm not sure if it's another group within EPA or it's or if they're different groups, but there's a development looking at a 1600 series method, again, working with DoD. And the last information I got on this was that it was going to be potentially for 40 compounds, which would be good. So kind of shifting gears now. So a lot of interest in background contamination, and really these low detection limits aren't new. We've been looking for dioxins at orders of magnitude below what we look for PFAS. However, we really weren't looking, sampling mainstream for PFAS, like dioxins like we are for PFAS. And the other thing, thankfully, is dioxins aren't widespread sources of contamination. So that put those together, and this is where all the concern around background contamination. And as Anthony discussed, this is just a composite do's and don'ts. You can find these in many regulatory websites. And again, just highlights the concern about background contamination. So this study that we did was a joint effort, by TRC and Alpha, and it was subsequently published in the Remediation Journal. And I'd like to acknowledge Liz Denley and Mike Everly and Nadal Rabah from TRC, as well as Phil from Alpha. So this work really grew out of a bunch of informal discussions. There's lots and lots of guidance as to what you should do and what you shouldn't do as far as sampling goes, but there really wasn't a lot of data. So we were curious, designed this study with a worst case scenario type of approach to see if we would detect anything really. The work was done in a series of 7 batches, essentially in our spare time. So this was an aqueous leaching study, not an extraction or a direct assay approach. So we used commercially available spring water, all obtained from the same source. As you might imagine, water was analyzed continually as blanks throughout the study to make sure it was PFAS free. And we used 250 mLs of water for the leaching of the product, and we leached them in the sampling containers that we typically use for PFAS as well. So again, this was very conservative. The procedure consisted of a 24-hour contact time on a shaker table. Ideally, everything was leached in replicate. It wasn't always the case, but most of the time we tried to do that in replicate. And we also tried to standardize the amount of material we leached. However, this really wasn't possible given the wide variations between the things we looked at. A lot of leaching blanks, as you can imagine. We also wanted to look at bentonite. And we looked at two types, a coated and an uncoated one. We had to change our leaching procedure to essentially putting it in a metal pan and adding the water. And when the bentonite started to expand, we essentially removed it. And then from there on, we used our standard prep. So our high-tech shaker table and our source water. So this was, again, solid phase extraction, LC-MS-MS, using essentially our laboratory proprietary method. We looked at 24 compounds. And the blanks were all clean. There were a few samples that were pretty problematic. We were looking at essentially sample bottle labels, but the adhesive would come apart, and that caused a lot of difficulty with the analysis itself. So we didn't really get good data there. And also a level C protective suit, in quotation fingers, that also the fibers on that would come out, and that made the analysis pretty difficult as well. So just looking at some of the data, PTFE, these are replicates, and as you might imagine, we got a pretty wide gradient of PFAS compounds being present in this tubing. And LDPE, a similar range, though significantly enriched in the C4 and C5 carboxylic acids, which was, I guess, somewhat of a surprise to us. And so when you look at the comparison between the two, you can see, the longer chain ones weren't as prevalent in the LDPE, but certainly the shorter chain ones were. We looked at bladders from pumps, and a lot of pumps, as I became more familiar with them, a lot of them had PTFE bladders. And so got similar data between the bladder and the tubing, I guess, as you may expect. But we looked at a number of bladders and different sets of tubing and got pretty consistent results, I'd say. We looked at water level tapes. There were 3 different types that we looked at, and 2 of them had detections. Baler line. What was interesting with this is we had both PFOA and PFAS detected in these samples. We looked at field books, and I think what was interesting to me on this is that the formulations of the chemicals used to prepare the pages were different than what was used on the cover. A significantly different PFAS signature for each. However, again, both were detected. So these are some of the things that we looked at that we didn't have any detects on. And I think at this point, what I wanted to stress is, so these were analyses at a sample that was obtained off the shelf from a manufacturer on a particular time, particular lot number. So this aluminum foil that we had on that day did not have PFAS detected on it. But that's not to say that all aluminum foil doesn't have PFAS. And the reverse is also true. Some of those products that we looked at that had detections of PFAS, that was specific to a specific, manufacturer, batch, and date, and other types of tubing of similar size made out of the similar materials may or may not behave the same way. So it really is the Wild West out there. And I think just from as Anthony went through, I think preparing a sampling plan and starting with, common practice, standard industry practice for site characterization in general, and then make your additional PFAS accommodations is very good advice. I wanted to bring up as well that there was a study that just was published end of last year, I think, maybe beginning of this year. And this was a very detailed study done by some well-known researchers in the PFAS field. And they pretty much did a much more comprehensive study than us. And for the most part, they had some things that with detections, but for the most part, things were showing up clean, or at least, at a detection level low enough that it wouldn't be considered a threat to contaminated sample. And that's something that I wanted to just finish up on. You should always make sure and make a difference between what comes in contact, what is in direct contact with the sample. And those are the things that you really need to focus on. I know the state of Michigan, they have a guidance, and they actually divide things out between materials that become in contact with the sample and things that don't. Other states may have similar guidance. That's very good rules to live by. And obviously, if your clothing or whatever really shouldn't be good standard practice, really shouldn't be coming in contact with your sample anyway, versus the type of tubing or the type of pump you're using obviously is. So always keep that in mind. And then lastly, and this is just anecdotally, so all of the blanks that people have been incorporating in their sampling programs, field blanks, trip blanks, equipment blanks, for the most part, and again, anecdotally, for the most part, these are coming up pretty clean. So that also would tend to support the fact that if you use your due diligence and sample correctly and have good standard practice for sampling, irrespective of PFAS, chances are not going to have a major contamination issue. And that's all I have for you. Thank you.
Great, thanks, Jim. That was interesting, and we've gotten some questions for sure, and people can type in some more. Someone's wondering if the Vinton O-rings of the pumps were looked at for cross-contamination.
We did not look at, I think, Viton or Viton. We did not look at those specifically, though I do not know if that other paper I mentioned, whether they did or not.
Okay. How about thoughts on why the LDPE contains PFAS, the low-density polyethylene?
I don't know why, except to say that if you look at all of the guidance, as far as sampling containers and sampling equipment, everyone says to stay away from LDPE. So it must be something in how the low-density polyethylene is manufactured that more susceptible to having PFAS bleed.
Okay. Let's see here. There's a couple analytical questions that we'll get to afterwards. Did you test for PFHXS and PFHXA in your studies, because trace levels seem to be very common in water sample results?
Yes, those two compounds were included on our list. I couldn't tell you right off the bat what we found there, but I could give you the reference to our paper and all the data's in there.
Okay. How about the pizza box? What type was it? Because, yeah, I put that in my compost. Other people do too. So the cardboard.
Well, you know, the pizza box was funny because that was lunchtime during one of these sessions. Around and said, well, you know, just for giggles, let's leach a portion of the pizza box. And we found, I believe we found PFOA and PFBA, I believe, in it. You know, it's hard to say. Obviously, that was an imported pizza box, you know, because we're not using the at least PFOA anymore. It wasn't made in the United States. And though it's hard, you know, did it come from the inks that was you know, the box was printed with? Did it come from the coating that those boxes are treated with to make them, you know, essentially water and grease resistant? Don't know. And I wish I could tell you exactly like which section of the box that we clipped out, but that is lost to time, so I'm not exactly sure.
Okay. Do you think your findings are generally support the do's and don'ts for PFAS sampling? And did you test any of the personal care products that everybody says to be careful about using?
You know, we wanted to include personal care products in this list. However, due to, as you can imagine, if you're trying to analyze bug spray or cosmetics or you know, hair shampoo, a lot of more analytical difficulties associated with that. And so we figured we would start with simpler things, you know, pieces of plastic and the like that would be easy to leach and would essentially be a proof of concept as to whether or not you can leach these things. So we started off with the easy stuff, and then I'm sorry to report, never really got to those materials. So I think that would be a good study, but on the other hand, maybe the approach of that subsequent paper where they were doing direct analysis might actually be better analytically than trying to leach those types of materials.
Okay. Now here's a couple of the more analytical questions. In a tandem MS, how do the two MS instruments divide their applications? What does the first and second MS do differently?
It's a good question. Well, I don't know if you're familiar with like GCMS and full scan mass spectrometry, where the instrument runs a range of atomic mass units and scans up and down. And so that's why with a VOC analysis, for example, you can get a whole list of compounds. But sometimes the client or regulator will come back and say, you know, I really need a lower detection limit of vinyl chloride. So what the chemist will do is, okay, well, I'm not going to scan for the full scan. I'm only going to scan for the masses that are associated with vinyl chloride. I'm just going to stick right there. So instead of wasting all that time going up and down, I'm focusing on that specific mass, and I'm getting a lower detection limit. Now, the way a tandem mass spectrometer works is similar, the same concept. So you look, the first stage, sample comes through, and the molecules get broken apart into reproducible pieces, and there are representative masses for each compound that we're looking for. So it's like that SIM, selected ion monitoring type approach. However, the second stage is that there's then a reaction where there's a collision and there's a reaction, and those essentially fragments then recombine into another mass that's detected in that the second stage mass spectrometer. And that's why this procedure is so powerful, because you've got the mass spectrometer, during the initial stage, but then after that reaction, you now have the second mass spectrometer looking for those reproducible daughter products. And so you put the two together and you know that, yes, this is the right retention time and the initial mass and the daughter ions all match, and I know this is PFOA. So that's the use for that. And when you're thinking, looking down to parts per trillion, you really do need to have something that certain.
Okay. Then another question is, what was the mass of the analytical subsample tested using the different methods? Is it 10 grams?
Oh, good question. We were trying to standardize on like 10 by 10 centimeters, like a square area, but that quickly became difficult when looking at tubing and things like that. So we tried to, 10 by 10 was essentially the benchmark, but there was some significant variation, I'm sorry to say.
Okay, in the mass.
Well, in look at mass, we were looking at area.
Okay. Okay, and then another one is, I'm not sure what this one means exactly. Were blanks subjected to granular activated carbon or ion exchange resin?
No, because the blanks were all the blanks were consisted of the same water that we did the leaching in, and we continually analyzed those blanks throughout the process just to make sure that we weren't contributing any PFAS to the study. But all that water is laboratory prepared, PFAS free, and it goes through our deionization and carbon treatment.
Okay, one, I think, well, maybe this is the last one for drinking water. Maybe you said 533 is superior to 537.1, but both of them could be used to look at 29 PFAS. Is that correct?
Yes, that's exactly. That's what I said. 533, in my opinion, is superior. Just looking at it academically from a an analytical method point of view, just because it uses isotope dilution, which is big, and I prefer that cartridge. The wax cartridge, I believe, is just more amenable to a wider range of compounds than the dibenzene one that's associated with 537.1. The difference between them, and this is a key difference, is that they don't look at the same list of compounds. 533 has a longer list, but there are some 537 compounds that aren't on that list. And going back to what I said about the 500 series methods, you're not allowed to modify them. So you couldn't do a 533 and add in those 10 compounds or whatever that are missing from 537. You couldn't do that. Well, you could do it, but you couldn't call it 533, let's say. So that's the big difference. So if you've been analyzing for 537.1 and you have a big, long data set over time for those 18 compounds, you switch to 533, you'd get more compounds, but there'll be some missing. So you have to make sure that you're aware of that. And yes, if you did want to do compliance analysis, drinking water compliance analysis with EPA standardized methods, and you wanted the maximum number of compounds, you would run both methods and you'd get 29.
All right. So I think we got to most questions, and we're coming right up on 3 o'clock. So I think this makes a good time to end. I really want to thank Anthony from New Hampshire DES and Jim from Alpha Analytical for their presentations. I will be posting PDFs of their presentations on the NEMOA website either later today or tomorrow, and we'll send out an email to everybody that was participating today with the direct link. But I did show you where you can get to all kinds of information about past presentations that NEMOA's had. So you can also just navigate there and on the NEMOA website and find them as well. So with that, I think we'll end today. So again, thank you again to Anthony and Jim. Bye, everybody. And thank you to everybody that attended today. Have a great rest of your day. Bye-bye.